first, just wanted to obviously the title gives it away. Macroscopic modeling for systems. There was a lot there was numerous directions that Monica and I could have taken this lecture in, and for two reasons we chose to do it through an example. First reason, we thought that is often, the most engaging way of doing it, and secondly, rather selfishly, it's where we've done lots of work ourselves. So our group in mechanical engineering is part of the bigger electrochemical science and engineering group, which spans the design school with Billy, who's just joined. Hi, Billy. Earth science engineering with Nigel Brandon, and chemical engineering with Magda Tutrisi, and a number of us in mechanical engineering. The majority of our work is on batteries, although we also do fuel cells, supercapacitors, redox flow cells, etc. And a lot of the problems we solve at the system level, where we have to do macroscopic modeling, is on lithium-ion batteries. So basically, the lecture course is about macroscopic modeling of lithium-ion batteries for systems. Obviously, if you're not interested in batteries, you're interested in fuel cells, redox flow cells, or anything else, similar techniques apply. When you look at how fuel cells are modeled at the system level, we have to do similar approximations, lumped parameters for, bulk phases and reactions and interfaces and things like this. So similar philosophies apply, but obviously if you're interested in those technologies, we're giving worked examples of the lithium-ion battery. I wasn't sure exactly what you've been, how the other, I haven't had a chance to I've dipped in and out of some of the other lectures, but I haven't had a chance to listen to them completely. So I don't know whether the style of this one is different or not, but either way, it is what it is. And we're going to be squeezing a lot in. So, the intention is this is a starting point. And if you're interested in anything, then basically this is a starting point for your own learning objectives. Feel free to get in touch if you think you might be interested in the kind of research we do and you're doing something similar, etc. And also, I wasn't exactly sure whether you'd been taught specifically how a battery works. So I thought just before I go into the macroscopic modeling, we'll just do a 5-minute maximum overview of what a lithium-ion battery is. So, hopefully you're all familiar now with the concept of electrochemistry requiring two electrodes, an anode and a cathode, where electrochemical reactions take place, redox reactions. One needs to be a reduction, the other an oxidation. Change the flow of current and you swap the electrode at which reduction or oxidation is occurring. In a lithium-ion battery, those actual reactions are of Li plus an electron going to Li some kind of intercalated or alloyed species. In the example of a solid-state battery, actually lithium metal. So what we're doing is reducing or oxidizing lithium from lithium 0 to lithium plus, or something close to lithium 0 if it's intercalated into carbon, or alloyed into a material like silicon or something like that. This diagram here on the right hand side is showing you an example where the blue anode on the left might be carbon and you're intercalating between the layers, effectively the graphene layers that make up graphite. And on the left hand side is the structure of a cylindrical cell, and I'll just show you a brief video. Let me just check that before I press play, I'm just going to check that when I share the screen, I include computer sound. There we go. So you should be able to hear this. It's a couple of seconds before the narrative starts.
Rechargeable battery cells are manufactured in cylindrical or prismatic cells, as this animation illustrates. First, copper is rolled into a foil that serves as the current collector on the anode side. Aluminum is used on the cathode side. Next, the electrode is deposited onto the current collector foil. The anode is typically made of graphite and the cathode of lithium-containing oxides or phosphates. The electrode coating goes through a drying step in which unnecessary solvents are removed and the slurry-based coating is solidified. After drying, the two electrodes come together in a sandwich structure with two separators, shown in green, positioned in between. This flexible layer structure then goes through a winding process and forms what is called a jelly roll. For prismatic cells, these structures are cut and layered, flatly rolled, or Z-folded. Next, the jelly roll is packaged into a cylindrical container that resembles an oversized AA battery. Here you can see the internal structure consisting of the two current collectors with electrode and the two separators for avoiding a short circuit. Before sealing and crimping the container, the battery is filled with liquid electrolyte. It is critical that the electrolyte wets the separator and fills all pores, leaving no or minimal voids in the separator foam. 8 to 12 cells are packaged in a module. Then 8 to 12 modules are packaged with a battery management and cooling system. Such a battery pack can then be used in plug-in hybrid and all-electric vehicles. The same or very similar battery packs can be used for stationary storage to enable intermittent renewable energy sources such as wind and solar.
Great. Okay, so that's the examples in there are not exactly state of the art at the end, but it gives you an overview right from the start to the finish of how a battery is made. Obviously, there's a clarification. They refer to anodes and cathodes. We all know that the anode and cathode are defined by the direction of the current, but it's convention in the lithium-ion battery industry to call the negative electrode the anode and the positive electrode the cathode, even though obviously the definition of anode and cathode does change when the direction of current changes. But it's just convention. So the negative electrode, which in a normal lithium-ion battery is carbon, is always called the anode, and the positive electrode is always called the cathode, even though that's technically half the time incorrect. Right, how do we move on? Okay, so looking at the principle of operation, what I'm going to start with, I'll just skip this slide. So the structure of this lecture is now going to be based broadly upon that video, essentially. Starting, you make the electrodes, you put them on layers. On the left is a cell that we disassembled once in a fume cupboard. In the middle are some pouch cells, and on the right hand side of the middle photo is a module, which in this case is 4 pouch cells. This is a Nissan Leaf battery, and then on the right hand side you can see these tins of 4 pouch cells, which are sometimes called a prismatic cell, are arranged in various configurations inside a battery pack for an electric vehicle. I'm actually going to do it in reverse. So we're going to start with modules and packs, and we'll work our way down to the cells and the layers. The reasons for doing this is we're going to start with the simplest models that we use, the simplest macroscopic models, and then as we get down to which are mostly empirical models, and then as we get down to cells and layers, when Monica will take over, we're going to start going to the more complicated models where we actually use physical models. So by physical models, I mean models where we use physics, as in equations, chemical equations, electrochemical equations, and we solve them in order to describe the behavior of a battery. So it just makes, I can start with the simplest models. As we go down the length scales to the smaller and smaller subunits, the models can get more and more complicated. So, we had a video there. So how is a battery pack made? We've already said it's made of lots, tens or probably hundreds, in case of a Tesla, thousands of individual cells, all connected together. This is just an example of a Formula Student vehicle that we built, some undergraduates built alongside myself and a few others. I think Billy may even have been involved. I don't know whether this was just before or just after his involvement, like mine, in Formula Student. In this pack, we had over 500 cells arranged into 2 side pods on a small electric single-seater race car. This, you know, the modules, so there were 3 modules in each side pod, so 6 modules in total. And you can see the modules were arranged in 12 cells in parallel, so we call that 12P, 7 in series. So it's a 12P 7S module. Now, when we made this, you know, and the cells are shown up the top, they're just a 5 amp hour little pouch cell. This was one of the very first battery packs we ever made in Formula Student, and also, you know, myself, that I was involved in designing and making. So we learned a huge amount. And what I always used to like to say, and still like to say about my involvement in Formula Student, you know, nowadays I'm much more hands off. I just supervise the occasional group of third years designing the next generation of battery pack for the university's Formula Student team. I don't run the team itself anymore. I stopped doing that quite a few years ago. But when I ran the team, and we eventually sort of like, I think we've ended up making 8 or 9 generations of battery packs. And I'd like to say we've never made a good battery pack. We've always made, you know, a battery pack that can be improved, and we've learned a huge amount from it. So actually physically making stuff has taught us a lot, and actually resulted in peer-reviewed journal papers like the one I'll show you here. So you can see the link down there. So we had, when we first tested this pack, we had a problem that we encountered. You can see on the left-hand side a red line, which is a individual string of 12 cells. We were measuring the voltage of each string of 12 in parallel. Because in theory, their voltages are all the same if they're in parallel. Now, in practice, that's not always true, because you've got interconnect resistances between the cells. But when we were designing the pack, we didn't realize that that was a significant thing we needed to take into account. But what you can see here is that that red cell, or the cell shown with the red line, that strip of cells strip 7, module 5, basically hit the voltage cutoff before all the others did, and that shut the vehicle down. So it meant the vehicle would have stopped on the racetrack too early. We wouldn't have been able to finish the event. So we were obviously concerned. We tried to get to the root cause of what was doing this. So we applied something called a differential resistance test. We looked in the test data for regions where the current had changed by a large magnitude over a very short period of time. And that's essentially like a pulse, like a current pulse, which is what we use in the lab to parameterize our models. I'll explain that a bit more detail later. But in the data of the vehicle being tested on a dynamometer, we could look for one of these events. And what we could then do is, simply using Ohm's law, calculate the differential resistance for each of those strips where we had a voltage measurement, because we knew the current through all of those strings of cells, the 12 cells in parallel, but then they're all in series. So all the series strings had to have the same current flowing through them according to Kirchhoff's law. And here we're plotting the potential drop, and you can see that that strip 7 had a much bigger potential drop for 160 amp current spike than the others. So if we use this to calculate a differential resistance, which is shown on the right, you can see we had a massive outlier. So there was clearly a problem with that string of 12 cells in that module. All the other modules, okay, there are a few other smaller outliers. We could explain that. This one was a problem. So we actually took the cell apart. Sorry, not took the cell apart, took the whole battery pack apart, took the modules out, and made the students disassemble it. And eventually we found that the metal blocks that were making electrical connection between all of these cells, one of them had a little grubby fingerprint on it, which left just a monolayer of glue, and meant there was a really high interconnect resistance. So essentially 2 out of the 12 cells were doing all of the work, and the other 10 cells behind that resistance were, you know, shielded from doing much work because they were stuck behind the high resistance. And so 2 cells were doing all the work, most of the current. There was a much bigger voltage drop through those 2 cells that we were measuring. And it just so happened that our voltage measuring was on that side, the 2 cells that were doing all the work, rather than the other 10 cells that were, you know, electrically isolated. So obviously we stripped that, we cleaned that off, reassembled it, and the problem went away. What we then did is we did a modeling study. The reason for showing you this is, as an example, is because we did modeling. And here we actually used MATLAB Simulink So we used a part of it called SimPower Systems, and we built a model of one of those entire modules. Why? Because we wanted to know what would have happened if we hadn't resolved that problem. Simon, sorry, could you just mute yourself? Thanks. And you can see here that, we've got a grey rectangle, which is our model of a cell, and I'll tell you a bit more about that in a second. And then you can see all these individual resistances that we had to add to model the actual physical reality of a battery pack, where you've got bits of metal, bus bars, connections, you've got interconnect resistances, where you have to connect two materials together, and you have to model all of these. Because if we didn't model this physical reality of the battery pack, we would not have been able to reproduce this phenomena that we had observed. So it's really, so the key learning point here is you have to model everything. You have to model the physical reality. You cannot just model a battery and extrapolate that to the behavior of a pack. And what we did here, we then ran a simulation, and you can see here that on the left-hand side was the current distribution that we were predicting from the model. Notice the scale changes. So on the left-hand side, we're going from 9 amps to 18 amps. On the right-hand side, from 6 to 36. So black on the left-hand side is not as bad as black on the right-hand side. Now you can see here that in this module, you can still see we've got some current distributions that are not uniform, and that's bad. You want uniform current distribution. You want all of the cells to be working equally. Otherwise, some of them might age faster than others. And you can see that we had a fundamental design flaw in the module, even if there were no problems with assembly. And this was because we were pulling the current from two corners, and we had relatively high interconnect resistances between the cells. They were comparable in magnitude to the resistance of the cells themselves. So it caused these current inhomogeneities. But on the right-hand side, you can see that if we introduce just one high interconnect resistance out of, in this pack of 84, we would have had in this single module, we would have had 168 interconnect resistances. In the battery pack of the whole vehicle, we would have been approaching about 1,000 interconnect resistances. So the chances of us having one dodgy interconnect resistance is quite high. We had one. We put it in, and you can see we could immediately reproduce the behavior that we'd observed experimentally just by introducing one artificially high interconnect resistance in the location that we found it when we stripped down the module. Then we looked into this, the fundamental design flaw. We looked into it a bit more, and actually this is a paper by Billy who's online, and he came up with this analytical expression showing that whenever you have cells in parallel, more than two cells in parallel, you will always have this unequal current flow caused by basically the current can find different pathways, and the current through the resistances between the cells affects the current through the individual cells. So that you can see the equations when you write the Kirchhoff's laws for the individual cells, they are not the same. They do not have the same number of current terms in them. So this is the net result. This is where the design flaw came into, and this does affect every cell, every pack that has multiple cells in parallel. Interestingly enough, also cells that have multiple layers in parallel, which is basically every cell that's ever been made. So you get the same problem in a cell as you do in a pack. You can solve this problem, but the only way by solving it is to keep those interconnect resistances very low. And general rule of thumb is if they're 2 orders of magnitude or less, 2 orders of magnitude lower or less than the impedance of the cell itself, then you can kind of ignore it. But if they're of the same order of magnitude or within an order of magnitude, then you have to take this into account and you have to model these effects. If we look at, can you avoid the problems by building larger cells? Well, this is the same study, but we had 6 cells, which we assumed were 10 amp hours instead of 12. You can see we still have the same problems. And then we took the model of the original pack with the dodgy interconnect resistance, and we put it through. We ran the current profile that we had from the race. So we went to the race, we'd solved the problem, but we simulated what would have happened if we'd gone to the race without dismantling the module and and making good that assembly problem. And essentially, we predicted that those two cells that would have been doing all of the work, the vehicle probably wouldn't have reached the voltage limits. You know, if we'd fully charged the pack, it would have gone around the racetrack. But after about 500 seconds, those cells would have got so hot, they probably would have gone into thermal runaway. So if we didn't solve this problem, you know, we predicted, obviously we never wanted to validate this. We didn't test whether our prediction would come true because we didn't want to set our vehicle on fire. But we predicted that if we hadn't taken that corrective action, that vehicle would probably have burst into flames on the racetrack. And that would have been caused by just one single grubby footprint of glue, causing a high cell interconnect in a battery pack of over 1,000 cells. Just one problem could have caused it to burst into flames on a racetrack and potentially harmed someone. So this is an example of a sort of like the biggest macro. This is kind of the biggest macro scale modeling we do in our group. It's sort of at the battery pack scale, and the purpose here was to show you the importance of taking into account all the stuff outside the cell. So this is, you know, what would have happened in terms of temperature and current. So simple calculations, we could use them to choose the pack configurations. We can obviously use models of this type for pack design. We could have redesigned the pack to avoid those current distribution problems, you know, the fundamental design flaw. Okay, we decided that was too much effort. It was okay. We could survive with just the design flaw, but we couldn't have the fault case. Let's look at cells. You know, I showed you this diagram. I said the gray box is a model of our cell. Well, what is the model of the cell that we used? What went here? So for the paper that I showed you, we just used MATLAB Simulink. It has a generic battery model that you can just drag and drop from SimPower Systems in Simulink. You just drag it in, connect it up. It has some terminals. You can see the plus and the minus. You know, so we spent a long time connecting up many of these in to make that battery pack. Did it the hard way. You can do it much more efficiently, you know, by coding rather than using the graphical user interface. And you can see here is what's inside that battery model. And at its heart, if you sort of if you just look in the bottom right, because everything around it is to do with how the model works. But you can see essentially we've got a controlled voltage source and an internal resistance. We have nothing more complicated than a Thevenin model. You know, a voltage source and a resistor in series is a Thevenin model. Now, it's a slightly more advanced than just a static Thevenin model. The voltage source is a variable. It's not a constant voltage source. And the internal resistance is also a variable. It can be a function of things like temperature. You can see around it, you can see if you follow that top arrow, you can see essentially a Coulomb counter, a current sense, you know, and we're using some various control loops just to basically control that voltage source. You've got to look up, you've got a Coulomb counter that counts how much current has flowed through and moves you up and down a voltage curve, basically. Not much more complicated than that. And then, as I said, the resistance in this model, I think, was only a function of temperature, nothing else. So we call that Thevenin model, we call that a 0th order battery model. But if we want to introduce some dynamics, you know, because obviously if we put a current change on a Thevenin model, the voltage response is instantaneous because we only have a resistor. Now, a real battery has some dynamic behavior. You know, the voltage changes slowly because, as you know, it has a double layer capacitor in it. So the electrodes are charged. The voltage, the actual voltage of the battery, is because of a charged electrochemical double layer. Now that double layer has some capacitance. Also, you know, we have a chemical reaction. So you can imagine a battery, so the chemical reaction keeps the double layer charged. At steady state, at open circuit, at equilibrium, you know, the double layer is fully charged. You reach the maximum, you know, steady state voltage of the battery. If you just measure it with the multimeter, you'll, you know, fully charged lithium-ion battery about 4.2 volts. when you start to discharge the battery, you are electrically discharging those capacitors, and then there is an electrochemical reaction that is continuously recharging those double layer capacitors. But you have to perturb equilibrium, which means you have to move away from equilibrium in order for that chemical reaction to have a net forward reaction. And so you have some voltage losses, but those voltage losses manifest over time because you're drawing down initially on the energy in the double layer capacitor itself. So we model that by introducing transients, by introducing capacitors into our equivalent circuit network models. So we can put one RC pair, we call that a first order model. We can put two RC pairs, we call that a second order model. And what we do is we add RC pairs to introduce time constants. So we might have a really small capacitor and resistor to model charge transfer resistance, because the time constant for that is going to be tiny, probably measured in milliseconds. And then we might start to want to mimic or emulate or model the diffusion of lithium ions intercalating into and out of the carbon structures or the mixed metal oxides or metal phosphates on the positive electrode side. And so we do that by introducing a larger capacitor or even a chain of RC pairs, which can basically mimic diffusion. I say mimic diffusion, then it's kind of not a truly physical representation, but it has been shown that they can be equivalent under certain conditions. So we introduce these RC pairs. So how do we parameterize it? Well, you've had a lecture or two, I believe, from Sam on EIS. So one of the methods we use to parameterize these equivalent circuit network models is electrochemical impedance spectroscopy, or EIS. So we introduce, so we subject the battery to a series of sine waves at different frequencies with a small amplitude. We can do this at open circuit voltage. We can also do this under load. We can do it with a constant DC offset. But then you have to make sure that each EIS experiment is pretty quick. You can't really do the low frequencies because otherwise the state of charge is changing. The battery state is changing during the EIS experiment, which can give you weird results. So you can do it at open circuit. That's more straightforward. But actually, because the charge transfer resistance is a function of current, it is helpful to do some experiments under load as well. So we do these experiments. I won't go into the detail because Sam has gone over EIS. And then we basically fit our equivalent circuits, the resistors and the RC pairs, not the voltage source, because EIS is not not giving you the actual cell voltage. It's just giving you the voltage response of the processes within the cell. So we don't fit the OCV part of our equivalent circuit model. We basically just fit that to a really slow charge discharge. But the resistances and the RC pairs, we fit to the impedance spectra. So if we had an impedance spectra which looked like this, you'd have to be pretty darn lucky to get one that looks like this, because there's no diffusion tail, there's no impedance. The high frequency intercept gives us the pure resistance, and then the other intercept gives us the resistance of the charge transfer resistance or the resistance of the RC pair, and you can fit and you can extract those parameters. So then we put all these parameters into a lookup table, which then, or we fit an expression to them, and that becomes our model. The high frequency intercept, the series resistances, is just a lumped sum of all of the ohmic style all of the resistances that behave in an ohmic fashion: ionic resistance, electronic resistance, etc. This is what a real lithium-ion battery might typically look like, and this is the typical model that you'd have to fit to get a good EIS fit, but we're not going to use all of these parameters in our models. We don't need the inductance, and we typically don't include the Warburg impedance. This is how how these values vary with things like frequency, with state of charge, and so you can imagine that these resistance values and these RC values have to be often a 3 or a 4-dimensional lookup table, where the resistances and the capacitances are varying as a function of temperature, state of charge, current, and maybe even something else as well. So these are just examples of how they're changing, and obviously we can begin to extract the relationships of how these parameters are changing, and fit them to some of the physics-based models, the equations that we put into our physics-based models as well. So this is also a route to parameterize some of the equations in our physics-based models, such as the Butler-Volmer equation, or the Arrhenius relationship, the temperature dependence of some of these parameters. The alternative way of fitting to EIS, and this is probably more common because this requires less sophisticated equipment, is to do pulsing. So pulsing is it's basically like hitting the cell with all of the frequencies at the same time. So it's like a bit like a very crude version of EIS, but we get these recoveries and these decays of the voltage, and we can fit those to the simple R and RC pair models. So in exactly the same way, we fit the model to the data, and we extract the parameters that goes into the actual cell model itself. So this is just an example of a paper we've done recently that just references some useful methods of doing this. The codes that you use to do the fitting are actually quite critical here. The standard method is called the layered method. You'll find references to that in this paper. And there's also, sometimes here this paper was about the fact that you can see two different time constants when you're doing the decay under load versus the relaxation. And this is caused because the different processes are dominating during the, building up of a diffusion gradient inside the cell versus the relaxation of that diffusion gradient. And, there's also some other interesting stuff going on that I won't go into, but feel free to read the paper and the references therein. So that's the sort of like going from the pack level model to a very simple cell level model, which you would be surprised at how common they are. Industry use those type of equivalent circuit models a lot because they're computationally very cheap. They're also relatively straightforward and to parameterize. So you can parameterize that style of equivalent circuit models from a cell without taking it apart, without any knowledge of the chemistry, how it was made, what went into it. So this is why they're so attractive, because if you've got an NDA with a battery cell supplier and the cell supplier NDA says you cannot take apart this cell or do anything that would be considered reverse engineering, then you can't physically dismantle it. You cannot therefore measure most of the parameters you need for the really good, powerful physics-based models. Therefore, this might be your only choice. So they have numerous advantages, but they do have some disadvantages. One of the biggest disadvantages is the lack of thermal discretization, but you don't need to go to full thermal, full physics-based models yet to do thermal discretization. So I've called this to lump or not to lump, because all the models I've shown you previously were making what we called a lumped thermal approximation, which is where we lump the entire cell and imagine that it has uniform temperature and everywhere is at the same temperature and all heat generated is dissipated uniformly. Now that's clearly a pretty bold assumption to make, and in many cases it's therefore wrong. So what can we do instead? And also why do we care so much? Why is that assumption so wrong? Well, it's because of this exponential relationship with the cell impedance and temperature. So on the left-hand side are some impedance spectra. I'd already shown you some on a previous slide showing how much the cell impedance varies as a function of temperature. You can't quite see the scale, but the coldest temperature there was about minus 8 or something, and the hottest temperature was plus 55. So we're going across about a 60-degree temperature window, and the cell impedance is varying from about 250 milliohms to 2.5 milliohms. 2 orders of magnitude change in the cell impedance across a normal operating temperature window. That is, from an engineering point of view, a nightmare, because this device is going to change its behavior by 2 orders of magnitude, and you're going to have to accommodate that in your pack design, in your thermal management, etc. So on the right hand side, you can see we've plotted this crudely. Impedance is red, and you can see it going, from by 2 orders of magnitude. But then you can also see a blue line, which is sort of like a crude, everything lumped together rate of degradation. So you can see that, you want to keep your cells as hot as possible, so the impedance is as low as possible. So you're having the least losses. It actually means the least heat generation, so it's easier to thermally manage and more efficient, but not too hot that your degradation is going excessive. Now, go too cold and you have both problems. The degradation rate goes high again for a different reason, different degradation process, and also the impedance is high. So really, you want to be operating in that Goldilocks region in the middle, around about 25. 25 to 35 is probably your optimum operating point for a lithium-ion battery with a normal commercially available electrolyte. Some cells are designed to operate hotter. What does this have effect on the cell performance? If we had those temperature differences inside our battery pack example that I showed you earlier, then those current distribution problems I showed you would have been even worse. Cells that got hot first would have then had a much lower impedance and generated more current than the colder cells until they discharged themselves, because they would be discharging faster, and then eventually they would, the colder cells would have to take over. This has a dramatic effect on performance. Essentially, if we look here, these are some experiments we did quite a long time ago. It's kind of a seminal publication from our group on the effect of different thermal management strategies on degradation. And we took a simple cell, the same cell as that battery pack was made with, as a pure coincidence, and we did tab cooling versus surface cooling. So there's different ways that we can cool the cells. In theory, at the time, everybody still mostly does do surface cooling, because you've got a large surface area, you can pull the heat out more easily. Problem is, if you think of how the cell is made with layers, this exacerbates the thermal management, the thermal gradient problem. The inner layers get hotter and I'm cooling the outer layers. And so by the end of a discharge or the end of a charge, the inner layers have exhausted themselves, the hot layers, and I'm now trying to pull all of the current through a small number of cold layers. And so you reach a voltage cutoff sooner. And so essentially that means you have a significantly lower usable capacity. You can see that the surface cooled cell, you can see the starting point at 0 cycles. When the two cells were identical, I could access only about 90% of the capacity compared to a tab cooled cell. And then this also gives rise to positive feedback, and the cells degrade faster over time, because essentially I'm just pulling higher currents through all the layers one after another, rather than nice uniformly degrading the tab cooled cell. This isn't true for every cell. It depends upon the way the cell is designed. That cell was particularly well designed for tab cooling. Pretty much every other cell we've ever tested is not. So tab cooling is actually, although it should in theory be better, in many cases it's not better, but that's purely because of the way the cells are designed. This tells you why. Essentially, it's about thermal conductivity. The thermal conductivity for surface cooling through the layers, you've got insulating materials that the heat has to pass through, the separators, porous electrodes. Whereas if you look at a tab cooled cell, essentially you now have the heat flowing in the plane of the current collectors, which are metal foils. So you're now trying to conduct the heat through highly thermally conductive metal foils. And of course, the thermal conductivity is about 2 orders of magnitude better. Of course, surface cooling still might get you higher net cooling rates because the surface area is orders of magnitude better, but you have this problem of exacerbating unequal current flows. So I'm just going to skip these and get to the models, and skip this. This is how we model it. So what we do is, just like we had in the battery pack, now we go and treat an individual cell as if it's a battery pack. So we treat each individual layer, or in this case, regions of layers, because we also care about thermal gradients in the plane of the current collectors. We basically divide up the cell, we discretize the cell, and we make each region have its own model. And in this case, the model is a 3 RC pair, so a third order, equivalent circuit network style model, parameterized, with data at the cell level. So we have to be very careful when we're parameterizing the model that we have minimal thermal gradients. So we can take cell level parameters and then just divide them up by the number of unit cells. So parameterization has to be done a lot more carefully. And then we need to know a lot of additional properties of the cell that have nothing to do with the electrochemistry. So that whole region on the left-hand side and the unit thermal ECN, we need a lot of thermal conductivities, the different thermal conductivities in the different directions, the specific heat capacity of the cell, the lumped specific heat capacity of the cell. We also need to know the resistances of the tabs, both the electrical and the thermal resistances, the weld region, where the current collectors are welded to a tab. If there's a change in materials, we need to know the cross-sectional areas of those tab materials and exactly what grade of copper or aluminium they are. So in order to model this kind of thing properly, in order to get a good fit to experimental data, you've also got to have a lot of information on the mechanical construction of the cell inside the boundaries of the can or the pouch or the prismatic tin. So it's just as important as, the thermal discretization and the additional mechanical and thermal properties of the cell are, quite frankly, just as important as making the electrochemical model more complicated. There is no point, in my opinion, of swapping that equivalent circuit network model of the cell with a physics-based model if you don't take into account the thermal discretization and either know that you're in a set of conditions where you can ignore that, i.e. very low C rates where thermal gradients are minimal, or thermally discretize your model at the same time. Otherwise, you run the risk, the huge risk of over or underfitting your model, i.e. basically putting something into your physics-based model that shouldn't be there because actually it's caused by thermal gradients, and instead you're trying to account for it with something else. And that obviously is very wrong. So the thermal discretization is super important because we've shown that we can reproduce phenomena with very simple models by introducing thermal discretization that cannot be reproduced with physics-based models, or if you do, you would have to invoke crazy physics. So we've then used these models. So I'll finish just with an example, and then Monica will take over after a short break. So just to show you the power of these models, we've used these models to work with industry partners. In fact, we've just won 2 new projects. As of Friday, we heard that we were successful in winning 2 new projects to work with cell design companies to actually design, the next generation of lithium-ion batteries, which obviously is super exciting for us because, as I said, we've done a lot of research showing that you can significantly improve the thermal management of cells through cell design, yet very few cells that are available commercially do this. So we're hoping to work with some companies to actually produce cells that are better than all the other cells on the market, or most of the other cells. Actually, Tesla have done a pretty good job on their latest cylindrical cell already. So this was an example of a study we did where we physically we commissioned some cells from a German company called Custom Cells, who will make you whatever you want if you pay them enough. We got them to build us 3 different lithium-ion batteries that were identical in every way except the tabs and how they were tabbed. So we had 2 tabs on one side, 2 tabs on the opposite sides, and 2 much wider tabs on the opposite sides. We did this to validate a model. So we parameterized our model for this cell, and we changed in the model. The only things we changed were the tabs and the parameters describing the tabbing and the mechanical and thermal properties of the tab region, the welds, etc. And then we compared it to test data, and you can see the test data for tab cooling of those 3 different cells, and then surface cooling of those 3 cells. They were more or less identical, so we just showed one. Surface cooling them was the same, basically. So we then, once we'd validated the model against those 3 different examples, so we could prove that the model was a suitable tool for doing cell redesign studies. We then looked at the variables that we had varied experimentally, and we extrapolated them a bit further. And then we tried some variables that we hadn't commissioned because the company couldn't make cells with significantly thicker tabs. So we varied tab thickness. And we showed that for this particular cell, tab thickness was the real bottleneck for this particular cell and the way that it's constructed. Essentially, the cross-sectional area of the tabs was not sufficient to get enough heat out quickly enough. Just by putting the tabs on opposite sides helped, making the tabs wider helped, but that only doubled the cross-sectional area. Whereas if we made the tabs thicker, going from 0.2 millimeters to 1.5 millimeters, we could increase the cross-sectional area by almost an order of magnitude, and we could approach the cooling rates that we could achieve through surface cooling through the tabs for this cell. So we predicted that this would be a vastly superior cell. So what I'm going to do is there's another example. I'll probably just finish this and then we'll take a break, and then I'll hand over to Monica. So we also did an example with a cylindrical cell. So I'll just rattle through this because this is similar to the other one, where we did the same kind of discretization, but now we have to do it radially because you have a spiral. So lots of nodes, the cylindrical part. The mechanical and thermal properties of cylindrical cell are, again, just as important as a pouch cell. If anything, in this case, a bit more important. They have a substantial impact in the results. If you just model the jelly roll region without modeling the can and the connections and the air gaps and the fluid gaps and the welding, then you get very, very different results. It turns out that for most cylindrical cells, they're just tabbed in two positions. So all of the current has to flow all the way around that jelly roll and just come out at one point. That doesn't seem very sensible when you think about it, and the models justify that guess. That essentially the more tabs you have, the better. You can substantially decrease heat generation. It doesn't have a huge impact on the heat rejection because the heat rejection for these types of cells is already pretty good. And there isn't that big a distinction between tab and surface because the can is the base, which is one of the tabs. But we showed that there's a substantial impact on inhomogeneities and therefore usable capacity. We haven't done the degradation study on a cylindrical cell because we haven't got cells with different number of tabs. Unsurprisingly, that's quite difficult to come by. Where everything else is the same. You can buy cells which have different numbers of tabs, but they're made by different manufacturers, different materials, so there's no direct comparison. But we can extrapolate it and assume that that more tabs is better for degradation as well. And we actually, in this modeling study, we couldn't get our hands on one, although I did email Elon Musk, and amazingly enough, he did reply, but he said no. I did ask if we could get hold of one of his new 4860 cells, where they basically come up with what they call a tabless, but what I would call just a continuous tab. So all of the current collectors of the negative and positive electrodes stick out all the way, and they just mash it all together and connect it somehow to the base and the cap at the top. So they basically just have, the current does not have to flow around the jelly roll at any point. It just has to flow up or down to the two tabs. Of course, that significantly reduces heat generation. We predict it will also significantly improve heat rejection, and that's what we wanted to do. We wanted to measure something that we've come up with in the group called the cell cooling coefficient, which I won't go into, but there's a YouTube video if you want to learn more about it. So we think they've probably come up with something that's pretty close to the optimal design for a cylindrical cell, but nobody's done that for pouch cells or prismatic cells yet. So, we are going to be working with industry partners to significantly improve the design of those form factors as well.